Hello everyone, I'm Rémi Portelas, and in this video I will briefly present our survey on automatic curriculum learning done in the Flowers Lab at INRIA in collaboration with Microsoft Research and OpenAI. So the first question is, what is curriculum learning and why do we want to use it when training autonomous agents? A typical example of curriculum learning is how human infants self-organize the development of their sensory motor skills. For example, before learning how to run, human infants go through a curriculum of increasingly harder tasks, starting from crawling, walking with help, then without help, and finally, they learn to run. The proficiency at which a child learns these complex skills hints that the secret recipe for training high-performance autonomous agents is likely to include some form of curriculum learning. And this intuition dates back at the very least to the 50s. At this time, Alan Turing was already thinking that to create an adult-level machine, the best solution might be to start from child-level machine and then give it an appropriate course of education. And the first use of curriculum learning for artificial agents seems to date back to 1985. In this Ishkai paper, Selfridge and colleagues trained a cartpole agent using what they called learning schemes. More precisely, the focus of our survey is on automatic curriculum learning, ACL for short, which are approaches adapting task selection with limited human help. We argue it is much more desirable than classical curriculum learning because gathering expert knowledge on a problem is time-consuming, it has to be redone for each new problem, and again, it looks like children can generate their curriculum by themselves, as when they engage in play without human supervision. They don't wait for us to tell them what to do. In our work, we define ACL for DeepRL as being a family of mechanisms that automatically adapt the distribution of training data by learning to adjust the selection of learning situations to the capabilities of DeepRL agents. For instance, an ACL algorithm can be used when training a DeepRL agent over a distribution of mazes to solve. In that case, it can adapt the task sampling distribution based on the history of the agent's performances. Before giving a formal definition of ACL, let's first quickly discuss the DeepRL learner setup. Usually, the DeepRL agent interaction with a given environment is framed as a Markov decision process, which is characterized by a 5-tuple composed of the state space, action space, transition function, reward function, and initial state distribution. And from now on, let's refer to this environment also as being a task. The objective of the DeepRL agent is to learn a policy pi that maximizes reward collection on the task. And given this, we can specify variants of the classical single task setup. For instance, Multitask Learning, which is a training regime where an agent has to learn a policy to maximize reward collection on a set of different tasks. And there's also multi-goal DeepRL, a variant in which a goal space J is added to the MDP tuple, and the objective is to master multiple MDPs varying by their goal. Another important precision for this talk is the difference between on-policy DeepRL, which learns from data collected with an up-to-date policy pi, with off-policy DeepRL, which can learn from interaction data originating from any policy. Note that in practice, off-policy DeepRL decouples interaction from learning, collection from exploitation. Given this, an ACL algorithm can be formalized as a task selection function, which adapts the distribution used to sample tasks for the DeepRL agent based on the history of past interactions of this learner. The optimization objective of such an ACL algorithm can be formalized as the maximization of post-training performance of the learner over the target task distribution. In practice, because this objective is hard to optimize for directly, all current ACL approaches use surrogate objectives, such as maximizing local learning progress, for example. In our survey, we propose to classify recent ACL works using 3 different viewpoints. First, we sort current works based on the main motivation that led them to use ACL. Was it to foster generalization, or maybe to solve a single very hard task? Then we look at which aspect of the learning scenario is controlled by the ACL algorithm. In practice, it means which parts of the task's MDPs are being adapted throughout training. Finally, we look at what is the nature of the optimization objective used by each ACL approach. Is it learning progress, or maybe diversity? And given these three axes, we survey most recent ACL works and compile our analysis into a big table. For time's sake, in this presentation, we'll go over this literature only through the last two proposed axes. Note that in parallel of these three viewpoints, we organize ACL works in two different subgroups. Data collection ACL, which refers to classical ACL approaches that are about choosing which tasks the learner will interact with, and data exploitation ACL, which are complementary variants suited for off-policy deep reinforcement learning. Here, instead of selecting tasks to interact with, they control on which tasks to learn from. So what can an ACL algorithm control? Let's first start with data collection ACL, which is about controlling parameters of the tasks being proposed to the learner. More precisely, this control can be applied over all MDP components. For instance, with the initial state distribution, this is what is done in a 2017 article by Florence and colleagues, where they propose reverse curriculum, an ACL approach which controls the initial arm position of an agent for a manipulation task. By starting first close to the target and then going backward based on the evolving agent's performances, they create a curriculum of auxiliary tasks allowing to ease the learning of the original MDP. ACL can also be applied to control which goals to propose to a deep-while learner. This is, for instance, what is performed in the Curious Architecture from Kola and colleagues, where they control which action should be tried on which object of the scene for each new episode. ACL has also been used to complement the reward function of a given task's MDP, often to ease learning in hard exploration scenarios. This is, for example, the case of the random network distillation algorithm presented by Birla and colleagues, which gives reward bonuses to an agent based on prediction errors of a network over visual features. The gradual learning of the predicting model pushes the agent to explore the environment for new visual features, which often aligns well with performances, as in Montezuma Revenge. A growing body of research is also looking at using ACL to control the selection or even the generation of environments. This is, for example, what has been done in OpenAI's paper on solving a Rubik's Cube with a robotic hand. In that case, they proposed ADR, an ACL algorithm adapting the domain randomization range for sim-to-real robotics. Finally, ACL can be applied to control the transition function of a given MDP, which often translates to control opponent generation, as in self-play works. This led to impressive results, such as in the well-known works by Silver and colleagues, in which they train AlphaGo and later AlphaGo Zero, both of which challenged and surpassed professional Go players. In the end, every aspect of the MDP can be leveraged by ACL algorithms to adapt what is proposed for interaction to the learner. And now, let's quickly look at a complementary toolbox, which is applying ACL for data exploitation. This is mostly relevant for off-policy learning, where there is a replay buffer accumulating experiences to use and reuse for gradient updates. The first aspect of off-policy learning that can benefit ACL methods is for transition selection in the replay buffer. Instead of randomly selecting transitions, an ACL algorithm can bias this selection based on the learner's performances. This is, for example, what is done by prioritized experience replay, a well-known approach to bias sampling in the buffer based on the temporal difference error of a Q learner. Another way to apply ACL for an off-policy agent is to modify transitions within the buffer. This implies to be in a multi-goal setting, as when doing object manipulation, for instance. The idea behind this technique is simple. If you did not manage to complete the goal you were targeting, well, then let's pretend that you were trying to reach the goal you ended up reaching. This allows to learn from rewarding transitions instead of having the buffer filled with zero reward transition that do not allow meaningful gradient updates for the agent. This makes transition modification very appealing in sparse reward scenarios. This simple yet powerful idea was first proposed and tested in the Insight Experience replay paper from Andrikovic and colleagues. Okay, so far we've seen that ACL can be used to control many different parts of the learning journey of an agent. Another viewpoint to survey recent works is to look at what are the proxy objectives currently being used by ACL algorithms. And here the real question might actually be, what is an interesting task? The first natural option is to optimize for tasks of intermediate difficulty. The motivation behind this is to avoid proposing either trivial or infeasible tasks. It often ends up being implemented by specifying an intermediate reward range and biasing task sampling such that the agent's performance fall within this range. This idea is at the basis of the reverse curriculum approach or the ADR algorithm we both mentioned previously. Optimizing for intermediate difficulty can give very good results, although it does require a lot of expert knowledge. It can also get stuck in sampling tasks of intermediate difficulty for which the agent cannot improve, which is a waste of learning time. An alternative to intermediate difficulty that has been proposed as a way to avoid these limitations is the use of learning progress as a driver for task selection. The main idea behind learning progress is that a task worth focusing on is a task for which an agent is progressing on. And absolute learning progress is a variant that also classifies tasks for which the agent's performance is decreasing as being interesting. This allows to detect and deal with catastrophic forgetting, which is a well-known issue for deep RL agents. Using learning progress does not require a specific intermediate reward range. It just needs to record empirical performances and analyze their evolution with respect to a given task or task distribution. There are many recent works that used a learning progress as a proxy objective, for instance the curious architecture I mentioned previously. It has also been used to select on which levels of a game to train on, and beyond discrete task sets, learning progress has also been used as an objective for ACL algorithm controlling task sampling within continuous task spaces, as for the LPGMM algorithm, which was used to help an agent generalize over a space of parkour tracks. There are many other surrogate objectives for ACL, like the adversarial reward maximization strategy used in self-play, the optimization of surprise often used for exploitation bonus generation, and others like optimizing for reward, energy, or diversity. I won't have time to discuss them, but I invite you to read our paper for more details. Let's now mention the main takeaways from our survey. ACL algorithms are becoming key ingredients for many deep reinforcement learning breakthroughs. More theory and comparative studies are needed, but ACL promises to bring deep RL into new challenging application areas where classical non-adaptive training schedules currently fail. Because it remains a relatively new field with multiple parallel lines of research, there are many potential combinations of existing works or even new approaches that remains to be tried. For instance, it could be interesting to see the impact of using ACL to control the body of the learner, like adapting its action space, its observation space, or even its learning capacity. ACL could control how much memory or compute the agent is allowed to use. There are also many ideas that remains to be tried. Maybe we could use learning progress to bias opponent selection in self-play, or maybe to sample goals in learn goal spaces. We invite you to read our survey paper to get an overview of what has been tried and shown to work so far, which can serve as a starting point for developing new insights and techniques. And with that, I thank you for listening.